first thing, whenever we're going to work on any electrical, make sure you wear your safety glasses, shut off the disconnect, and then test to make sure that each leg has no voltage to ground. First, our display should show next to no voltage at all. Because the disconnect is pulled, I'm going to first measure to a known voltage source just to make sure my meter's working, going from outside to outside, and as you can see, it's measuring 212 volts. Now I'm going to measure going to the unit, and as you can see, I have 0, but I still want to confirm that I have 0 to ground when I get inside the appliance, just to be safe. With the power safely off, now I can remove the electrical panel to gain access to all of the electrical components. Now we're going to do a safety check from each of our incoming lines here. This is L1 and L2 coming in to ground to make sure that we don't measure any voltage. I only use measurements from hot to ground for a safety test. I don't use them for diagnostic purposes. This is because these measurements can give you a false reading when you have a backfeed situation, such as in the case of when a disconnect or breaker only has one leg connecting. So safety to ground, yes. For diagnostic purposes, generally not, unless you're doing an ohm test to ground. Now once again, before you use a voltmeter, it's a good idea to just double check by putting your meter in the ohm scale, touching your leads together and confirming that you have continuity. This means that there's a path from one tip to the other tip of the meter lead. Let's take a look at the wiring diagram. In the case of our schematic ladder diagram, you can see this is our ground reference, and this is our L1 coming into the contactor, as well as our L2 coming into the other side of the contactor. We check these to each other to confirm for 240 volts. For a safety check, we check from here to ground as well as from here to ground to ensure that we don't have any potential that could cause an electrical shock. In the case of this contactor, it only has a single pole, which means as this switch opens, it shuts off the entire unit. We can check for voltage drop across that point, and it will measure the total applied voltage when the contactor is de-energized, and it should show next to no voltage drop when the contactor is energized. Just to identify quickly the components that we're looking at right now, this is the contactor, which is our main switch, and as you can see, it's already pulled in by a 24-volt electromagnet on the underside, which means that we have 24 volts applied across our contactor. This comes from our inside transformer and thermostat. Let's go ahead and just show this measurement. Whenever you have an energized load, you should read nearly the full applied voltage across it. And as you can see, we have 24.7 volts across this contactor coil, which is exactly what we would expect. This is our run capacitor. In order to measure the microfarad reading of our run capacitor, we could either do it while the system is running by using some basic math that we show how to use inside the HVAC School app, or we could disconnect the wire, make sure that it had no stored charge by jumping across it with a resistor, and then measure the microfarads. Every capacitor is going to have a microfarad reading on the data tag, and the easiest way to do it is simply to disconnect the terminals and measure from C to Herm and then C to fan on the dual run capacitor for your measurement. And now we're going to use our meter leads in order to check our incoming voltage as well as our voltage coming out of the top of the contactor, which is how you would confirm that you have potential difference being applied to the loads. Now, obviously we can see that our fan is running and we can hear our compressor running, so we know there is voltage applied, but this is how you would do this measurement. As you can see, we have 212 volts going into L1 and L2. We have 212 volts coming out of L1 and L2. A common mistake that technicians make is they attempt to measure across a switch. The voltage that's shown here of 0.3 volts is the voltage drop across the switch, and it's too small to even be accurately measured. It would be the same as taking our 2 meter leads and putting them in exactly the same position on the contactor. There's no potential difference between these 2 points, so I'm not going to get a measurement between them when I measure across the switch or at the same point. We'll do the same thing here and show you. It would only show a reading if we had a significant voltage drop. So now you can see we have 214 volts at the bottom of the contactor, like we would expect, but we measure nothing at the top. But that's not true that we have nothing, and this is where the safety test comes in. If I measure from here to ground, now you'll see that I still have significant voltage present there. So this would be a diagnostic test to show that there's no potential difference across these points because one of the legs is open. But we still have 120 volts present. Now our contactor coil is pulled out. You can see this position is now further out because the electromagnet's released because I've unhooked the 24 volts. So now coming into the contactor, we have 214 volts, and coming out now we read nothing because there's an open path, because this is no longer allowing any potential through the contacts. But this is still not a safe circuit, because if I measure from here, you'll see I still have 123 volts. And even on the other side, I show 123 volts because it backfeeds through the compressor back to this point. So a safety check is always to ground to ensure that you don't have any potential. Now, because this contact is open, I can measure across it, and there will be a potential difference across these 2 points, where before there was no potential difference. Again, one more time, now you see the contactor is pulled in, and now there's no voltage drop or potential difference across these 2 points. 212 volts coming in, 212 volts going out, which is what you'll show on a running unit. You'll also show a slightly higher voltage when you measure in between common, or the C terminal on your capacitor, and your HERM terminal. You see we have 295 volts. That's the voltage incoming plus some back electromotive force being generated by the motor that we see on the capacitor. We can use that calculation as well as our current from our HERM terminal in order to calculate the capacitance on our capacitor while the system is running. That's it. Thanks for watching. Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come.